Welcome back, students. Today we're going to be talking about function transformations. This is a bit of a challenging topic, and unless you've really understood the previous sections, you're going to struggle with this. So make sure that if you did struggle, go ahead and review some of the videos that you had more problems with, or review your notes from previous sections before we move on to this topic. The first part of this that we're going to talk about are the family of functions. Now, a family of functions is just a group of functions that have similar characteristics, such as the linear family of functions. They all have constant slope. The parent of a family of functions is the most basic form of that family. So the most basic linear equation is this: f of x equals x. Nothing more than that. So that's the parent function. The graphs of all other non-constant linear functions are just transformations of the graph of the parent function. Okay? So any other line is just some transformation of this original. A transformation changes the size, shape, position, or orientation of the graph. In this lesson, we're going to see how different numbers and signs put at different parts of the equation create these transformations, create a change in the size, the shape, the position, or the orientation of the graph. It's important that you be able to distinguish about how multiplying by a 2 creates a different type of transformation than does adding a 2. And that even where you add, subtract, multiply, or divide these numbers also makes a difference to what type of transformation occurs. The first transformation we're going to talk about is a translation. A translation is a transformation that is going to shift a graph horizontally, left or right, or vertically, up or down, but does not change the size, shape, or orientation of the graph. In the middle of these graphics, the black line represents our parent function, f of x. The red and the blue represent some transformation that has happened to that function. In this situation, we've taken f of x and we've made a little change. We are adding or subtracting some number to the input. Now, this subtle little change to the function creates a horizontal translation. Okay, now also notice down here, we get even more specific. If we're adding a number to the input inside of these parentheses, that takes this graph and moves it to the left. If we subtract h inside of those parentheses, that's going to move it to the right. Okay, now also notice the difference between what creates horizontal translations and what creates vertical translations. Now the difference is where this new number is occurring. In here, we were adding or subtracting it from the input. In other words, it was happening inside these parentheses. Whereas for the vertical, we're adding or subtracting just to the output. We're adding or subtracting it to the whole function. Now, if we add a number, now let's go ahead and say this was 2. I would take any number I had for f of x, and then I would add a 2 to it, and that would just move everything up. If I subtracted the 2, well, that would just move everything 2 down. And in that way, adding some number k will move the entire line k units up. Subtracting some number k will move all of it k units down. So these are the ways in which we create horizontal and vertical translations. So let's see some examples of what this looks like. I've got a f of x is equal to 2x minus 1. I want to describe the transformations from the graphs of f to the graphs of g and t. So let's see what g and t are. G of x is taking f of x and then adding a 3 to it. So we would take all the values we get from f of x and just add 3. T of x does something different. We take all the inputs that we have of x, we add a 3 to the input, and then we evaluate f with the new input of x plus 3. Now we are going to write equations for these. We're going to make tables of these and then graph them and then look at what type of translation occurred. To start off with, we're going to start with f of x. To make a table of it, I just pick any numbers I want for x, and then I put them into the equation for f of x and evaluate. So if I put in a 0, 2 times 0 is 0, 0 minus 1 is negative 1. And that's why here in the x we have a 0, in the f of x we've got a negative 1. In that same fashion, I found all of my f of x numbers. And now we're ready to graph them. Not all of them fit. I don't have a y is negative 5 on my graph, but many do. So at 0, negative 1, at 1, 1, at 2, 3, and at 3, 5. Now we can draw a line straight through those, and there is my line for f of x. Now let's go ahead and graph g of x. Pay close attention to how I changed this equation. Okay, so it said g of x equals f of x plus 3. And we know that f of x is 2x minus 1. So I changed f of x to 2x minus 1 and added a 3 to it. Okay, and then I simplified, and that creates the equation 2x plus 2. So here's my new equation that I can now use to make a new table for g of x, and then we can compare the two. So here's my g of x. I used the exact same x numbers as above. So if I put in a negative 2 into g of x, I get 2 times negative 2 would be negative 4, plus the 2 would then be negative 2. And so that's where I've got all these numbers for g of x. And then we begin graphing each of them, and we draw the line through them. Now we want to focus in on how did this change the green graph. So notice this. Every single blue dot is exactly 3 higher than all of the green dots. And that is because this type of transformation, where we just add a 3 to the outside, moved all of our numbers to be 3 higher than they were before, because we just took all of these f of x numbers and we added a 3 to them. And that's essentially the way that equation works. It's always just 3 more than the other. Okay, so this creates a vertical translation 3 up. T of x is going to work this way. Now, because we have x plus 3 inside the parentheses, we're going to change just x to x plus 3. So I've got my 2 times, and now rather than x that was there before, I now change it to the x plus 3 we saw there, and that is because it was inside those parentheses. And then the minus 1 that f of x also had. I can now simplify that by using distributive property, and I get 2x plus 5. I now put all of my x numbers into this 2x plus 5 to get these outputs. Okay, as a quick example, if I put in the 1, 2 times 1 is 2, plus 5 is 7. So when x was a 1, we see t of x was 7. Now that I've got all these numbers, I can graph my xy points. Negative 2, 1. Negative 1, 3. 0, 5. Okay, and those are about all that are going to fit. I can draw my line. Now we want to compare the red line to our green line. And we can see it is always 3 to the left. By adding a 3 to the inputs, we now create an equation that is always 3 to the left. Now, here's why that works. If I'm just adding 3 to the inputs, the first thing we do is we add 3 to the x's. Let's take this 0, for example. I'm doing 0 plus 3 would be 3. Now, if the input is now a 3, then it works like this. R3 for f of x gave us a 5. We see that 5 happening here at 0 because everything in t of x is going to happen 3 faster. Okay, we saw it happen 3 places earlier. This 5, 1, 2, 3, and that's where it showed up there. Okay, this 3, if we go back 3 places, we see that same thing. It's all the same numbers, but adding that number to the input just makes all of those outputs happen 3 places earlier. Okay, so that's a horizontal and vertical translation. Next, let's talk about reflections. Okay, reflections is basically flipping over a line. We are either going to reflect it across the x-axis, as you see here. You'll notice it's kind of a mirror image as we cross the x-axis. And that's going to look like a y equals negative f of x. We're taking our outputs, f of x, and changing their sign. Next, we've got reflections across the y-axis. Notice the difference. We still have a negative, only this time we're changing the inputs to negatives rather than the outputs to negative. When you change the inputs to negatives, it causes the reflection to occur across the y-axis. Okay, now let's see some examples of what that's going to look like. We've got f of x is equal to 1/2 x plus 1. We make our table just like before. Now that we've got our table, graph our points. Draw the line. Next, here's g of x. Now we've got the negative that's in front of f of x, so I'm going to rewrite all of f of x, 1/2 x plus 1, and I'm going to put a negative in front of it. And done. That's the equation. I just substituted f of x. And now I would go through the process of putting in all my x numbers. Half of negative 2 is going to be negative 1. Negative 1 plus 1 is going to be 0. Okay, so at negative 2, I also got a 0. But I just put in all these x numbers again so that I can get some outputs that I can now graph. And so there are all of my outputs for g of x. To do t of x, notice how the negative is now inside. I don't have an f of x, I now have an f of negative x, which means I need to take my original equation and change from an x to a negative x. Whatever is inside the parentheses, that's what you're going to change your original x into. So now I've got 1/2 of a negative x plus a 1. We take all of our x values, plug them into this formula, and that'll give us all the outputs for this function. So we get 3, 2, 1, 0, negative 1. And we draw the line. So now we want to describe the transformations of the graphs of f to the graphs of g of t. G of t, or g of x and t of x. So starting off with g of x, that's in the blue. Comparing these two, we can see they are reflections of each other across the x-axis. And that's because all these numbers are basically repeating, but just as negatives. We took the output, so the output for this dot right here is 3. But in our transformation of g of x, it happens at negative 3. Here we have a 2, it happened at negative 2. A positive 1, a negative 1. All of the outputs have just switched their sign. That creates that flipping across the x-axis. Whereas in B, notice the numbers in the red line and the numbers in the f of x line. Okay? Hopefully you've noticed they're exactly the same, just in a different order. And that's because of this negative. if I try to put in this negative into this equation, I'd get a negative of a -4, which is just a +4. And so now I'm going to get the same number as the first one would when it used a +4. So all my negative numbers are going to give me the same answers as what I got in the positives. And all my positive numbers are going to give me the same answer as what I got in the negatives. And so the red and the green form a reflection across the y-axis. Now, to know which one is which, pay close attention. I knew g of x was going to create a reflection across the x-axis because the negative sign is in front of the function, whereas here it's on the inside, and that created the reflection across the y-axis. Paying attention to where the negative is makes a big difference. Okay, horizontal stretches and shrinks, vertical stretches and shrinks. Now, the thing to understand is these are both going to seem very similar. And that's because they are. A horizontal stretch could be a vertical shrink. And I'll show you what I mean. So let's take a look at these two equations. These two graphs aren't exactly the same, but they'll illustrate the point well enough. We've got our base function. Now, here where it's pointing inwards, that's creating a horizontal shrink. Horizontally, meaning left and right, we are squeezing inwards. Therefore, we're shrinking inwards. Now, that same kind of motion over here could be shown as, well, we're also just stretching that upwards. So a horizontal shrink can be the same as a vertical stretch. Now, what can make a big difference is what it looks like in the equation. So here we've got f of a of x, and this is a of f of x, a times f of x. Where a happens makes the difference between calling it a horizontal stretch or shrink or a vertical stretch or shrink. Okay? Now, another thing to pay attention to, if you are multiplying the input by some number and this number is bigger than a 1, that will create your horizontal shrink. It's shrinking inward. Whereas if the number is between 0 and 1, think about a number that's greater than 0 but less than 1. It's probably a fraction, something like 1/2, 3/4. If it's a number like that, it creates a horizontal stretch. Okay? And always by a factor of 1 over a. So if I was multiplying the input by 2, that would create a vertical shrink by 1 over 2. Or in other words, by a half. Everything is shrinking horizontally by a half. Vertical stretches, very similar, only this time we multiply the outputs by a. Now, if a is greater than 1, that creates a vertical stretch. If a is some kind of a fraction, then it creates a vertical shrink. Okay, notice the similarities between these two. Also, they're pointing out something important. When you horizontally stretch or shrink something, the y-intercept is going to stay the same. Whereas if you vertically stretch or shrink something, the x-intercept is going to stay the same. Now, let's go ahead and look at an example. We've got f of x is equal to x minus 1, and we want to graph it. So, make our table from that function, graph the points. Now here's our first transformation. Notice this one has it on the inside. Since this is showing it on the inside, okay, that's going to mean that this needs to be a horizontal stretch or shrink because we are multiplying the input by 1/3. Now, because it's inside the parentheses, all we do is we change the x in the original to this new thing, 1/3 x. So we get 1/3 x minus 1 as compared to just x minus 1. Now that we've got our new equation, we can create a table for that. We plug in all the numbers, -3, -1, 0, 1, 3, and we get our outputs, -2, -1.3, -1, -0.6, and 0. Okay, and we can draw our line. So what we see from this is this has created a horizontal stretch. Our green line is being pulled at from its sides. Okay, and because this was a 1/3, it stretched it by a factor of 3. Everything is 3 times bigger. So here's what I mean. Here we had x equals 1. Blue had it over here at 3, at a number 3 times bigger. Same thing where we saw x being a -1 down here. It was back, the blue had it at -3. It was 3 times wider. It stretched by 3. Now we're going to multiply by a 3 on the outside of this. So we got 3 times f of x. So I'm going to take f of x, which was x minus 1, and multiply it by a 3. Notice the differences between what you do when it's inside the parentheses and when it's outside. We can distribute that through, or we could leave it like that. Either way, we just need to get a table out of it. Now that I've got my table from this new equation, I can graph my dots and put in the line. Now this is going to create a vertical stretch, meaning that rather than it being wider, it is now taller, so to speak. Notice how the blue kept the same y-intercept. The red is keeping the same x-intercept. And everywhere the green had a y value of 1, this is 3 times higher at +3. Here where it had a value of -1, it was 3 times lower down at -3, because vertically it's stretched by a factor of 3. Okay, so the green and the blue, once again, because it was inside the parentheses, horizontal stretch. Outside the parentheses with the red, created a vertical stretch. All right, horizontal and vertical shrinks. We've got our equation. We make the table. Graph all of our points. Draw the line. Here's our new equation. Notice we're taking f of x and turning it into f of 4x. So we change the x in the equation to 4x. Now we're ready to add those points to create a new graph. So -14, -6, 2, 6, 10. Put those dots on the graph and draw a line through it. Now, right now, what we can see, because it's on the inside, I know it needs to be horizontal. It's a number greater than 2, and I can also see it's taller. Therefore, this has stretched vertically. Okay, so this is a vertical stretch. Okay, here we're multiplying by a 1/4 outside of f of x. So we do 1/4 of x plus 2. So I just took whatever f of x was and I put the 1/4 in front of all of it. I make my table out of that, find those values, and start graphing them. Okay, we notice vertically that this created a shrink. Okay, everything is lower, and it's lower by a factor of 4. Okay, it's by a factor of a 1/4. So here where our y value is 4, down here it's at a value of 1/4. Okay, so the transformations of the blue, it was a horizontal shrink. Okay, a horizontal shrink. We took the green line and we condensed it inwards. Then for the red, it created a vertical shrink. We took the green line and we shrunk it down vertically. Now let's talk about combining transformations. If I've got f of x and g of x, describe the transformation from the graph of f to the graph of g. Now this goes back to what we said about the parent functions. This is the parent function, f of x. G of x is some linear function, and we want to identify what are all the transformations that happen that take us from the parent, f of x, to this child function, g of x. So let's start with just f of x, and I'm going to go ahead and graph it. And let's figure out, well, and here's g of x. We can graph that. Let's talk about all the steps in between. How can we start with f of x and do one transformation at a time to eventually create an equation that looks just like this blue one, g of x? One of the first things I notice is that negative. Okay, so right here in red, you see I've reflected my green equation across the y-axis. I also made sure that I put my negative inside of f of x. So that first creates this reflection. Now that I've got my reflection, if I multiply it on the inside by a 2, then I would get negative 2x, and that creates this horizontal shrink. It's squeezing inwards, which we notice that's kind of what that blue had. It had a different slope, more squeezed inwards, so I did a horizontal shrink by a half. Next thing, I notice my red line is still too low. It needs to be 3 higher. So what I do, I add a 3. And that's going to take the whole line, do a vertical translation 3 up, and those are the transformations that it took to take us from the green line to the blue line, reflecting across the y-axis because of that negative right there. Horizontal shrink by a half because we were multiplying by that 2 there. Vertical translation 3 up. Well, we just move it 3 up and then we're directly on it. I know this can be a bit of a challenge. I hope this helped you out. Good luck.